In August 2005, Hurricane Katrina made landfall on the Gulf of Mexico coast with winds exceeding 280 kilometers per hour. Most people remember the devastation it brought to New Orleans. What most people don't know is what happened 150 kilometers offshore, where hundreds of oil platforms sat directly in the storm's path. By the time Katrina passed, 115 oil platforms had been destroyed, 52 more had been severely damaged, 457 pipelines were broken, and the Gulf of Mexico lost nearly a third of its oil production overnight. The economic damage to the energy industry alone exceeded $15 billion. Today, we're going to answer the question that storm raised for the entire world. How do offshore oil rigs survive hurricanes? And what happens when the ones that can't, don't? To understand how oil rigs survive hurricanes, you first need to understand exactly what a hurricane does to the ocean. Most people focus on the wind, but for offshore structures, wind is actually the least dangerous part. The real threats come in three forms. First, wave height. A Category 5 hurricane can generate waves exceeding 20 meters in height. That is the equivalent of a 6-story building of solid water moving at high speed and crashing into a steel structure repeatedly for hours. Second, wave period. This refers to how frequently the waves arrive. During a hurricane, waves can arrive every 12 to 18 seconds. Each one transfers enormous force into the platform's legs and foundation. Over hundreds of hours, this creates something called metal fatigue, microscopic cracks that compound over time. Third, storm surge. Hurricanes push enormous volumes of seawater ahead of them, temporarily raising sea levels by 3 to 9 meters above normal. This means the ocean surface rises to levels the platform was never designed to handle. Combined, these three forces can generate lateral loads, sideways pushing forces, that exceed 50,000 tons on a large platform. To put that in perspective, that is the weight of the Eiffel Tower pushing sideways against your structure over and over again for an entire day. So, how do offshore engineers design structures that can withstand those forces? The answer lies in three engineering principles that most people have never heard of. And that took decades of costly failures to develop. The first principle is called pile foundation depth. Fixed platforms, the kind you see standing on legs in shallow water, are anchored to the seabed by steel piles, driven 50 to 100 meters into the ocean floor. These aren't just resting on the seabed. They are mechanically locked into the earth itself. Even when the platform above moves and shakes violently, the foundation stays fixed. The second principle is dynamic positioning and mooring for floating platforms. In deeper water, where fixed platforms cannot reach the seabed affordably, floating structures are used instead. FPSOs, semi-submersibles, and spar-buoys. These are connected to the seabed by massive mooring chains and cables, each capable of withstanding loads of thousands of tons. The platforms are designed to move with the waves rather than resist them, absorbing energy through motion rather than fighting it. Think of it like the difference between a rigid tree that snaps in a storm versus a flexible one that bends and survives. The third principle is called the 100-year storm standard. Every offshore structure in a hurricane-prone region must be engineered to survive what analysts call a 100-year storm. A storm so severe, it statistically occurs only once every century. The calculations include wave heights, wind speeds, and current forces, all happening simultaneously at their worst possible levels. After Hurricane Katrina proved that even that standard was sometimes insufficient, many operators upgraded their platforms to 1,000-year storm standards. This engineering does not come cheap. A single platform designed to 1,000-year hurricane standards can cost $2 to $4 billion to build. But engineering can only do so much. Before a hurricane arrives, the most important priority is getting people off the platform alive. Offshore evacuation is one of the most complex logistical operations in the energy industry, and it has to work perfectly under extreme time pressure. Here is how it works. The moment meteorologists identify a storm system that could threaten a platform's location, the operator activates what is called a tropical storm plan. This typically happens 5 to 7 days before projected impact, giving just enough time to act. The first 48 hours are dedicated to securing the platform. Non-essential equipment is shut down. Wells are capped using a device called a Christmas tree, a complex arrangement of valves that seals the wellhead against leaks, even if the platform above it is destroyed. Production pipelines are depressurized and isolated. Then comes the evacuation itself. Workers are flown off by helicopter in priority order. First the non-essential personnel, then the operations crew, and finally the skeleton crew that performs the last safety checks before departure. On larger platforms, up to 200 workers may need to be evacuated, with helicopters carrying 12 to 19 passengers and flying in increasingly deteriorating weather. This can take 18 to 24 hours of continuous flights. In extreme cases, where helicopters cannot fly safely, workers board enclosed lifeboats, capsule-shaped survival craft designed to be launched directly into hurricane-force seas and keep occupants alive even when fully submerged. The goal is to have 0 personnel on the platform by the time the storm arrives. During Katrina, operators evacuated approximately 90% of Gulf of Mexico workers, around 30,000 people. In the days before landfall, it was one of the largest industrial evacuations in American history. Despite all of this engineering and planning, hurricanes still destroy platforms. When a platform fails, the consequences extend far beyond the structure itself. The most immediate risk is an oil spill. When pipelines snap or wellheads are damaged, hydrocarbons, crude oil, natural gas, or condensate can escape uncontrolled into the ocean. Even a single ruptured pipeline can release thousands of barrels before emergency valves activate. After Katrina and the closely following Hurricane Rita, the U.S. Minerals Management Service estimated that approximately 124 spills occurred in the Gulf of Mexico, releasing a combined total of nearly 17,000 barrels of oil into the water. The environmental impact of these spills can last decades. Oil coats seabed habitats, contaminates fisheries, and affects coastlines hundreds of kilometers from the original release point. The economic impact is equally severe. When a platform is destroyed, the oil and gas it was producing disappears from supply immediately. After Katrina, Gulf of Mexico production fell by 1.5 million barrels per day, roughly 25% of total U.S. production at the time. This sent shockwaves through global energy markets. Petrol prices in the United States rose by 40 cents per liter within days of the storm, and rebuilding a destroyed platform takes not weeks, but years, meaning supply disruptions can persist long after the storm itself is forgotten. Katrina was a turning point for the entire offshore oil industry. In the years that followed, operators invested billions in improvements that fundamentally changed how offshore platforms are built and operated. Platforms in hurricane zones were retrofitted with stronger structural connections. New designs incorporated deeper pile foundations and more flexible mooring systems. Emergency disconnection systems were upgraded so that floating platforms could release and move out of a storm's path rather than remain anchored and absorb the full impact. Weather monitoring technology also transformed completely. Today, operators use satellite data, ocean buoys, and AI-powered storm prediction models to track hurricanes with far greater precision than was possible in 2005. Evacuation decisions that once had to be made based on 48-hour forecasts can now be planned using 7-day projections, accurate to within 50 kilometers. In the Middle East and Asia Pacific, where typhoons and cyclones pose similar risks to offshore operations, operators studied Katrina's lessons closely and applied the same improvements to their own platforms. Facilities like those operated offshore Abu Dhabi, including the fields connected to Dar's Island, which we covered in our last video, are now engineered to standards that account not just for current storm patterns, but for the projected intensification of tropical systems under future climate conditions. The ocean is becoming more dangerous. The industry is being forced to become smarter, faster. Every time you see an offshore oil platform on the horizon, you're looking at one of the most engineered objects ever built by human hands, designed to stand in water for 25 to 30 years, to resist waves the size of buildings, to keep producing through conditions that would destroy almost any other structure on Earth. And when nature sends something powerful enough to challenge even that, the people who operate these platforms have 48 hours to get everyone home safely and seal the well so tightly that even the ocean cannot open it. That is the hidden engineering behind the fuel that powers the modern world. If you want to see more videos like this, subscribe to Oil and Gas Explained. Next week, we are going inside the world's most expensive oil and gas project and revealing exactly how much it cost. See you then.